Hello, so this is the chapter 5 review, and chapter 5 is on nomenclature. Nomenclature is the word we use to say how to refer to the convention on how to name a compound and how to write their formula. There is a convention so that people from one end of the world can understand which compound we are referring to when we have a specific name and a specific formula, so that there is no mistakes. And so before we go over this review, I want you to take out documents from the Canvas homepage. So if you scroll down to chapter 5, the chapter 5 module, I want you to take out the periodic table, or have a periodic table open. You will definitely need that when you do a nomenclature. And also there is this document called Naming Compound, Flowchart, Prefixes, and Polyatomic Ions. You need that list of polyatomic ions, the prefixes, and a flowchart that's to help you as you learn. So let me show you those documents. So of course the periodic table, and then the other document is this. So the first page is showing you the list of polyatomic ion that you can watch. When you're looking for a polyatomic ion, go to that list. Some of them needs to be learned by heart, and we'll talk about that later in the review. And then you have the table of the prefixes to the right. That's for naming type 3 compound, which are made of non-metals only. And then the second page here is a flowchart to help you, use a systematic approach when you are trying to name compounds. So on the left side, it's how to name ionic compound, which are made of metals and non-metals, or two polyatomic ions. And then on the right, it's how to name covalent compound, which are made of non-metals only. Whenever you don't know what kind of formula you have, you always want to decide first, do I have an ionic compound or do I have a covalent compound? Because you will not use the same way of naming. And it's important from the start to use the correct rules. Because, for example, for covalent compound, we use prefixes. Otherwise, it's similar. The name of the first element is the same as it is in the periodic table, and the name of the second element ends in "ide." But for ionic compound, you need to decide if you have a type 1 metal or a type 2 metal. Type 1 metal are what I called up to now predictable ions, which are from group 1A, 2A, 3A for the metals, right? And the group number tells you the charge on the ions, on the metals, like lithium, magnesium, and then aluminum. And then there are some exceptions. The cadmium 2+, silver plus, and zinc 2+ are exceptions. They are always that kind of ion. So that's why there will be type 1 compound when you have these ions. And then type 2 compounds are formed from more than metals that are what we call variable charge metals. They are variable charge metals because they are metals that will make different kinds of ions. For example, iron can be a 2+ or a 3+. And so these are type 2 compound, and they will need a Roman numeral after the name of the metal. So let's practice this with the chapter review. So first question, what is the formula for these deeply blue crystals of copper 2 sulfate? What type of compound is it? Type 1, type 2, or type 3? By the way, type 3 are the covalent compounds, right? Type 1 and type 2 are written here in the flowchart, but type 3 are the covalent one. So we have this name, copper 2 sulfate. So you are looking at the periodic table to find copper. Copper is here, and the symbol is Cu. So we have Cu, and it says 2 in Roman numerals in parentheses after copper. So that tells you, and you confirm here from the position here, that copper is a transition metal because it's in those B groups here. B groups, you know, from 3B to 2B here. So it's metals that make more than one kind of ion, except zinc, silver, and cadmium, which are surrounding copper. But copper here needs a Roman numeral because it can be copper 1 or copper 2. So here, copper 2 tells you it's copper with 2 positive charges. That's what the Roman numeral tells you. It tells you the charge on the metal. Next, we have sulfate. Sulfate. You see the ending in 8, and so that tells you it's a polyatomic ion. If you look at the list of polyatomic ions, there are different kinds of endings, and the most common ones are 8 or 8. And these endings tells you you have a polyatomic ion, because the you know, ions that are just single elements, single anions, are ending in "ide". So whenever it ends in 8 or 8, you know it's a polyatomic ion. Of course, there are exceptions here. The hydroxide, if you look on the left side of the table here, the hydroxide ends in "ide" and it's a polyatomic ion. The cyanide is also an exception. And that's it. So these two are exceptions. They end in "ide", but they have a peculiar name that you need to recognize here. So sulfate, we are looking for sulfate. Sulfate is here to the left, towards the middle of the table. It's SO4 negative 2. So you want to write this down. SO4 negative 2. So when you are writing, this is an ionic compound, right? You see it's made of ions and metal and non-metals. Copper is the metal. So you always write the positive ion first and the negative ion second. So, you know, first the copper 2+ and then the sulfate. And then here you see that you have 2 positive charges from the copper, 2 negative charges from the sulfate. So they will cancel out. And so it's going to be simply CuSO4 together, right? Because the principle you're using when you are writing a formula is that you want the formula to be neutral overall, as many positive charges as you have negative charges. So now what type of compound is this? Well, it's a type 2 compound, right? Because copper is a variable charge metal. That's what makes it a type 2 compound. We have a variable charge metal, so we need a Roman numeral. Let's look at question 2. The formula for CaCl2 and COCl2 look very similar. What is the name for each compound? Why do we name them differently? So let's name CaCl2 first. So Ca, you recognize that on the periodic table, and that's calcium here, right? So you will write calcium, and then Cl is chlorine. So we have calcium and chlorine, a metal and a non-metal. So it's an ionic compound. Calcium is in group 2A, right? Which means it's a 2+ ion. So it's a predictable ion here because it's in group 2A. So calcium 2+, and Cl is also a predictable ion. It's in group 7A, and we do 7 minus 8, we get -1, and that's the charge on the chloride. So that justifies then this formula where you have 1 calcium with 2 positive charges and then 2 chloride with 2 negative, 2 times 1 negative charge. Anyway, the name will be simply a calcium chloride, because calcium is a type 1 metal. It's predictable ion, it's always 2+. So it's a type 1 ionic compound, and we don't need a Roman numeral. Now, COCl2. So CO, you look at your periodic table, and CO is cobalt. Cobalt Cobalt is a transition metal, as you can see. It's part of this B group or D block. So we will need a Roman numeral because cobalt is not an exception. So we need to decide what is the charge on cobalt to know what kind of Roman numeral we will need on cobalt. We have 2 chlorine in this formula, which will make 2 negative charges because chlorine we know has 1 negative charge, but there is 2 chlorine. So that's going to be 2 negative charges. So cobalt will have to cancel those 2 negative charges by being CO 2 plus, right? Because it's made of 2 chloride. So we'll have to have CO2 plus. So that means in the name, we will have to have cobalt chloride. Cobalt 2 to tell that we have the cobalt 2 plus ion and then chloride. Yeah, notice how we change the ending of the names for the second element or the non-metal, or as to "ide" when it's a single element like that. So that's a type 2 ionic compound because cobalt is a variable charge metal and we need a Roman numeral whenever we are using cobalt. So that's why the name of these 2 compounds are different. Calcium chloride and cobalt 2 chloride. It's different, especially from the fact that you need a Roman numeral for the cobalt and you don't need one for the calcium. So remember always to ask yourself, follow this flow chart and ask yourself, do I have a type 1 metal or a type 2 metal? Because, for the homework and the quiz, you will be expected to pay attention to all these details. So we are doing question 3 now. Give the formula and name of the 2 following molecules. So you have these molecules and you have a key to tell you what color of sphere is, what kind of atom it is. So we'll start with the first one that has 2 blue spheres bonded together, and then there are 2 red spheres bonded to each of the blue. So here, notice how it's nitrogen and oxygen. And if we look here, nitrogen and oxygen, they are both non-metals, right? One is here, the other is there. Both non-metals, which means it's a type 3 metal, a type 3 compound, right? Because it's made of non-metals only. When you have a covalent compound like that, you will need prefixes. Prefix, name of the first element, another prefix and name of the second element with the ending "ide." So we will use those prefixes here. And we saw that there was 2 blues, so that's the di prefix for this, for 2 atoms. And then we had 4 red, so tetra will be the prefix for that. So 2 blues, so that means di, and then N is nitrogen, so di-nitrogen, and then tetra, oxygen will become oxide. You change the ending to "ide", and oxygen is dioxide. So tetra oxide. However, here, pay attention to the fact that we are dropping the A of the tetra when it is in front of an O or another vowel. So it's not tetra oxide, it's tetroxide. This is important to remember this as you do the quiz and the homework. You need to be aware that we drop the A of tetra or penta or hexa when it's in front of another vowel. Okay, so then it's D-nitrogen for 2 nitrogen, and then tetroxide for 4 oxygens. If we look at the other model, we have the iodine and the chloride. And iodine and chloride are both non-metals as well, both halogens from group 7. So that's again a type 3 covalent compound, right? type 3 covalent compound, and we need prefixes. We had 1 blue and 3, forgot the color, 1 purple, 1 iodine, and 3 chlorine. So the prefix for chlorine is going to be tri for 3 chlorines. So we need, so now you need also to decide, do I name the iodine first or the chloride first? To decide that, you need to look at which one is the more metallic of the two. And here they are both in the same group. So is chlorine more metallic than iodine? So if you remember how the metallic character changes, let me put an arrow here. The metallic character changes this way. Well, the arrow is not correctly oriented. So, sorry, this way. Okay. That's the way the metallic character varies in the periodic table. In the upper right corner where is helium is the less metallic. And as you go to the lower left corner of the periodic table towards francium, this is more metallic. So the metallic character increases from right to left and from top to bottom. So iodine is more metallic than chlorine. So iodine will be the first element in the name. So it's going to be iodine, and there is only one. So we should use the prefix mono. However, when you have mono for the first element, we omit it completely. So we will not say monoiodine. We will just say iodine, and then tri, and chlorine will become chloride. So iodine trichloride. That's the name. Iodine trichloride. So these two were type 3 compounds. Let's do question 4. Write the process that shows the formation of the copper Cu plus ion from the copper atom Cu by adding or removing an electron to the following equation. I see how this can be misleading. We never actually subtract, we always add, but the way to remove an electron, for example, or add an electron will depend on which side of the arrow you put it. So let's look at copper here. Copper becomes copper plus. Copper plus has lost an electron, right? Because we have 1 positive charge from the fact that we have 1 proton in excess. And because we cannot change the number of protons, that means copper has lost an electron to have, a proton in excess. When you're losing an electron, you're not saying here minus 1 electron on the left side. What you're doing is you add an electron on the right side, plus 1 electron. That's the way we do this. Let me format this properly. So plus 1 electron, and this is going to be on the right side, because copper, when it became Cu plus, it lost this electron. So now you have the ion plus an electron, plucked away and separated from the copper atom. So that's how you should write it. Copper loses an electron to become Cu plus. So that's how it should be. Let me emphasize that this is what we added here. Okay, so now we have questions after that are asking what is the number of electrons in the ion and what is the number of electrons in the neutral atom. Let's answer that one first. Let's look at the periodic table for that. So copper is atomic number 29. That means it has 29 protons. So 29 protons, and when it's the neutral atom, it will have 29 electrons, right? Now, when it becomes copper plus, And we know it has lost an electron, so that's going to be 28. So that's the answer for these two. We have a similar question with question 5, but this time it's with sulfur. Write the process that shows the formation of the sulfide ion, the S-2 ion, from the sulfur atom, sorry, by adding or removing an electron to the following equation. So again, here, sulfur will gain 2 electrons to become S-2, right? We know this. It's a predictable ion. It's in group 6A, and it likes to gain 1 and 2 electrons to be like argon, right? And we know it's a predictable ion. We can do 6 minus 8 negative 2 to find the charge. So sulfur will gain 2 electrons. So how do we show this? Here, those 2 electrons are already gained, so they have to be added on the left side this time. So plus 2 electrons this way. So notice how it's always plus electrons, but what matters is if you put it on the left side, like here, it's going to be added. And if you put it on the right side, like in the copper case, that means you removed it. Okay, so that's how we show this. So now let's find the number of electrons in the neutral atom of sulfur. Sulfur is atomic number 16, so the neutral atom will have 16 electrons as well, 16 protons, 16 electrons. And when it becomes the sulfide ion, we know it has gained 2 electrons, so it's going to be 18, because we have 2 more electrons compared to the neutral atom. So let's move on to question 6. Question 6. Most metallic elements form oxides, and often the oxide is the most common compound of the element that is found in the Earth's crust. Write the formulas of the oxides of the following metallic elements. So if it was not obvious here, I want to show you that, first there was only aluminum, but what it means here, the question is asking for the compound named aluminum oxide, or zinc oxide. So let's do aluminum oxide first. We have metallic elements, right, form oxides. That tells you it's ionic compound, right? Because aluminum is a metal, right? Aluminum, be careful with aluminum, even though it's just touching the staircase on the top and on the right side here, it's not a metalloid. Aluminum is a metal, just like polonium is also a metal, even though it's touching the staircase. All the others like boron, silicon, germanium, arsenic, antimony, tellurium, and astatine are considered metalloids, but not aluminum and polonium, so be careful. Aluminum is in group 3A, right? It's a metal. So we know that group 3A metals are predictable ions, and the group number is the number of charge. So aluminum makes typically the aluminum 3+ ion. So we know that we have aluminum 3+ for the cation. And then oxide. Oxide, hopefully you recognize that this is the ion that comes from oxygen. So oxygen is in group 6A. So 6 minus 8 is -2. So oxygen always makes the O-2 ion, and that's the name, the oxide ion, O-2. Oops. So -2 is superscript in the upper right corner. Always write the cation first, then the anion second, right? Positive ion first, negative ion second. This is an ionic compound, and we can use what we call the crisscross trick. You see I have arrows prepared here. These arrows are used to do what we call the crisscross trick, where you will take the charge of one ion and it will become the subscript for the other ion. So that means aluminum here will give its subscript, will give its charge of 3 as a subscript to oxygen. So that's going to be Al3, AlO3, and then the 2 from the oxygen will become a subscript for aluminum. So then the formula is Al2O3. And it makes sense here if you check that the number of positive charges cancels the number of negative charges. So 2 aluminum with 3 positive charges each, so that's 6 positive charges in total. And we have 3 oxygen with 2 negative charges each, so 2 times 3 is 6 negative charges. 6 positive charges cancel the 6 negative charges. Okay, let's name the second one, zinc oxide. Again, zinc is a metal. Zinc is here. It's part of the transition metals. Notice how it is in a B group. However, zinc is an exception, along with silver and cadmium. Those 3 are exceptions. Let me emphasize that. Zinc is an exception, it's always 2+. Silver is always +1, and cadmium is always 2+. So those 3 are exceptions among the transition metals. They are always making one kind of ion. So there will not be type 2 compounds, but instead type 1 ionic compounds, right? So zinc, we know it's zinc 2+. Oxide, we already know it's O2-. So let me put the charges in superscript. And we can again do the crisscross trick. Or you can see also that 2 positive charges will cancel 2 negative charges. And here you don't really need, because, you know, it would be, I will format after that. So if I use the crisscross trick, it would be zinc 2O2, right? The 2 from the oxygen becomes a subscript for zinc, and the 2 from the zinc become a subscript for oxygen. However, you always try to minimize the set of subscript to the lowest whole number ratio, and 2 and 2 can be simplified by 1 and 1. But 1 and 1 are not written. We don't do that in chemistry. We often omit the ones. They are implied. So the formula is actually zinc ZNO, simply, because 2 positive charges cancel 2 negative charges. So one of each ion makes it neutral. So that's it for the zinc oxide. Let's do potassium oxide. Potassium is in here, atomic number 19 in group 1A. Group 1A are alkali metal. Alkali metal always make +1 ions. These are predictable ions, and it's +1. So that's K+ then, always for potassium. And then again, we have the oxide ion. So we write the oxide after that. You can use the crisscross trick. And you can see that the 2 from the oxygen will become a subscript for potassium. And then the 1 from the positive charge of potassium becomes a 1 for oxygen, and it's implied, we don't write it. So then the formula is K2O. And you see that indeed you need 1 oxygen ion with 2 negative charges and 2 potassium ions, each with 1 positive charge, so that they cancel, those 2 potassium ions will cancel the 2 negative charges on the oxygen. And here, just emphasizing the fact that aluminum, potassium, oxygen are all making predictable ions, right? They are part of, group 3A, 1A, this is 6A. Of course, oxygen is a negative ion, right? It's a nonmetal. So you can find their charge using the position in the periodic table. But zinc is an exception, even though it is a transition metal. So you need to remember about zinc, and we said silver and cadmium, right? So those three are exceptions among the transition metals. So question 7, what is a polyatomic ion? Give examples with names and formulas of 3 common polyatomic ions. So you have this table of polyatomic ions. Again, that's in your Canvas chapter 5 module. And it will be provided for the quiz, for example, of this week. It will be, in the upper part of the quiz. So there are a few ions in there that you need to learn by heart. And I will list them in the answer. These are the ammonium, the nitrate, the sulfate, the hydroxide, OH-, the phosphate, PO4 -3, and the carbonate, CO3 -2. And I think the hydrogen carbonate could be added there too. So these are the ones I want you to remember. First, let's answer that question. What is a polyatomic ion? A polyatomic ion is made of several atoms bonded together by covalent bonds. Ions are, species that carry positive or negative charges. So it's an ion with positive or negative charges, but it's made of several atoms because poly means several, atomic refers to atom. So it's made of several atoms bonded together by covalent bonds, right? It's this type of bonds, not ionic. So they will behave just like those ions we've seen above, the zinc 2+, the O2-, except that the formula will have more than one type of atom. And so here I'm showing a few here that I want you to remember. The ammonium, the hydroxide, OH-, the nitrate, NO3 -1, carbonate, CO3 -2, phosphate, PO4 -3, sulfate, SO4 -2. These are the ions you need to remember. And I think you can add also the sodium, not the sodium, sorry, the hydrogen carbonate. So that answers question 7. What is the formula of ammonium phosphate? So we just saw above that ammonium is a polyatomic ion with formula NH4+. And notice, by the way, how ammonium is the only positive polyatomic ion. Notice everyone has negative charges except the ammonium. The first listed in the upper left corner here is the only one with a positive charge. So it can form ionic compound with other polyatomic ions or single anions because it's positive. And here we have ammonium with the phosphate, and the phosphate here is just here. It's PO4 -3. So we have ammonium and then the phosphate. And because it's 2 ions, we always write the positive ion first, then the negative ion. And so together, they will form this formula. So you use the crisscross trick. You have to be very careful when you use the crisscross trick with polyatomic ions. It's really the charge. So here, ammonium has 1 as a charge. So that's going to make only 1 phosphate. And then the phosphate has 3 negative charges. So that will make it 3 ammonium. And whenever you have more than one polyatomic ion, you need to use parentheses. Notice how we do not use parentheses when you have only one of the phosphate. Only one of a polyatomic ion doesn't require parentheses. But if you have more than one, then you have to have parentheses around the polyatomic ion symbol, and then a subscript to the right of the parentheses to say how many of that polyatomic ion you have. And here it's 3 ammonium for 1 phosphate. You see that you need 3 ammoniums to cancel, to have 3 positive charges to cancel the 3 negative charges on the phosphate. So that's why here it's going to be ammonium phosphate with 3 ammoniums per phosphate. And so it's an ionic compound, even though it is made of nonmetals only. Right? It's made of nonmetals only, but it's an ionic compound because these polyatomic ions behave like ions. So it's an electrostatic attraction between positive and negative charges that creates those compounds. So that's really an ionic bond between ammonium and phosphate. So question 9, name the following compounds. First indicate the type of compounds they are. Type 1 ionic, ionic type 2, or covalent type 3. It is important you decide the type of the compound before you try to name, otherwise you will apply the wrong rules and then the naming will be wrong. So the first step is to decide, do I have an ionic compound or a covalent compound? And then if you have an ionic compound, is it a type 1 or a type 2? So here, boron and oxygen. Let's look at the periodic table. Oxygen is a nonmetal and boron is a metalloid. Metalloids with nonmetals form a covalent compound, right? This is covalent compounds, even though it says non-metals only, it's also including the metalloids. So this is a type 3 covalent compound here, because it's made of a metalloid and a non-metal. Okay, so then we need to follow the flow chart here on the right that says we need prefixes in front of the element's name. And then the second element should have the ending "ide." So the prefix for boron, so B is boron, will need to be di, right? If you don't know the prefixes, 2 is di, and then 3 is tri. So we need di, boron, and then tri for 3 oxygen, and oxygen becomes oxide. So it's going to be diboron trioxide. Diboron trioxide. Okay, let's look at what we have next. Oops. CuSO4. I wanted it to be CrSO4, sorry. CrSO4. Cr is chromium, right? SO4. SO4 here is nonmetals, and that's a metal, right? Chromium is a metal, it's a transition metal. So that means it's an ionic compound, metals and nonmetals. It's an ionic compound made of chromium transition metal. So this is going to be a type 2 ionic compound because we have a variable charge metal there. So type 2 ionic compound because we have chromium. Chromium is a transition metal, so a variable charge metal, and it can, because it can make different kinds of ion. So that means we have a type 2 ionic compound. We recognize SO4. SO4 is one of those polyatomic ions, and we have it here just above. SO4 with 2 negative charges is the polyatomic ion named sulfate, and it carries 2 negative charges. Why do we need to know this? It is important because this is a variable charge metal, and we need to find the charge on chromium in this sulfate, because that will determine the name, right? We have a type 2 metal, and so we need a Roman numeral to say what is the charge on chromium in this compound. Because we have one sulfate with 2 negative charges, so we have 2 negative charges in total, and we need to cancel them with 2 positive charges. And we have only one chromium. Oops, sorry. So that chromium will have to carry the 2 positive charges. So that's going to be chromium 2 plus. There's only one sulfate, 2 negative charges in total that need to be cancelled by 2 positive charges. Sorry, that's chromium. Oops. Chromium will have to carry those 2 positive charges, and there is only one chromium. So it will be chromium 2 plus in this compound. So chromium 2 plus will be named as chromium parentheses 2 in Roman numerals, close parentheses. And then when you have polyatomic ion, you just name the polyatomic ion as it is in the table, the list. So that's going to be chromium sulfate, chromium 2 sulfate, right? You need to specify in Roman numeral the charge on chromium. Oh, sorry, it's copper, but here it should be chromium sulfate. Ah, no. Okay. Next one, Ag2S. So let's look at the periodic table for both of these. Ag, silver, we said even though it's a transition metal, it's an exception. It's always Ag plus. Sulfur is a non-metal in group 6A. So we have a metal and a non-metal. So this will make it an ionic compound. And because silver is a predictable ion because it's always +1, so that's going to be a type 1 ionic compound. So we know we have Ag plus and S2 minus. But yeah, so they are both predictable ion. So we don't need a Roman numeral. So you just name silver, and then S sulfur becomes the sulfide because you change the ending to "ide" for a type 1 ionic compound. Right, so that's going to be silver sulfide. About sulfur, I want to say something that is important here. Sulfur is with a F in the American way of saying sulfur. We spell it with a F. The spelling with PH is British, and you should not use that in this course. We are in America, so you need to use the sulfur with the F. This is important when you do sapling. The homework, you may have trouble if you're using the British version of sulfur with the pH. Same for sulfide or sulfate or sulfite. All of them needs to have an F, to be proper spelling here. So silver sulfide, a type 1 ionic compound, because we don't need a Roman numeral here. Silver is a predictable ion. Next, we have lithium. Oops. Lithium LiHCO3. So I told you already, this is lithium, right? We recognize lithium here. And then we have non-metals, hydrogen, carbon, oxygen, And this is actually polyatomic ion. Lithium is in group 1A, so it's predictable ion, it's Rs plus 1. So we will not need a Roman numeral, and so that's a type 1 ionic compound. So lithium is Li plus. Then you need to recognize this. So you go to your list of polyatomic ion, and HCO3 negative 1 is the hydrogen carbonate, or also called the bicarbonate. So we need that name because when you name compounds with polyatomic ion, you just take the name from the list of polyatomic ion. So HCO3 negative 1 is the hydrogen carbonate or the bicarbonate. So together it's going to be lithium hydrogen carbonate or lithium bicarbonate. And we don't need a Roman numeral because it's a type 1 ionic compound, right? Lithium is group 1A. It's a predictable ion. So that's an easy one. Next one, Cl2O. Cl is a non-metal, an halogen from group 7A. And oxygen is just slightly above here, also a non-metal. So they are both non-metals, right? So that means we have what we call a covalent compound or a type 3 compound. We will need prefixes in front of Cl and oxygen, and you name them in order that they are found in the formula. So first it's going to be chlorine and then oxygen. There was 2 chlorines, so we will need the prefix di, and then only 1 oxygen, so mono for 1. So let's see. We have a type 3 covalent compound, so it's going to be dichlorine. You keep chlorine the same way it is in the periodic table. So dichlorine monooxide. The ending of the second nonmetal is in ide. So dichlorine monooxide. Okay, let's move on to the next one. Oh, yeah, let me just add here. The more metallic element is always written first in the formula and name, right? And between chlorine and oxygen, well, it's hard to tell really because we said that the metallic character varies, from helium to francium, increases this way. And really oxygen and chlorine are, same level here, but because it's chlorine first in the formula, so you name chlorine first in the name. Okay, so let's see, we have CSBr next. CS is cesium. So be careful, cesium, it's CESIUM, and sorry, Br. Cesium and then bromine. Bromine is a non-metal, cesium is a metal. So we have an ionic compound. Cesium is in group 1A, so it's a predictable ion. It's always cesium plus. So that means it's a type 1 ionic compound. We won't need a Roman numeral. So you name cesium like it is, and you name bromine becomes bromide. So it's going to be cesium bromide. It's a type 1 ionic compound. And finally, we have FeClO4 2 times. Fe is the iron. Iron is a metal and it's a transition metal. So that means it's a variable charge metal. We will need a Roman numeral. And then ClO4. So this is a polyatomic ion. If you look at the list of polyatomic ions, ClO4 is called here in the middle of the slide, perchlorate, right? It's the perchlorate. Oops. It's the perchlorate, ClO4 negative 1. We have 1 negative charge per perchlorate. So let's summarize this. Fe is a transition metal from group 8b, so it's a variable charge metal. So that means we will need to decide what is the charge on Fe in this particular compound. So that's why we need to know what is the charge on the perchlorate. And here we have 2 perchlorates, right? There are parentheses and then a 2 outside the parentheses telling you there is 2 perchlorates with 1 negative charge each. So that means 2 negative charges in total in this compound. So we need 2 positive charges on that 1 iron. So the iron will have to carry 2 positive charges, right? These 2 negative charges need to be cancelled by the cation Fe, and there is only 1 Fe. So we will have to have 2 positive charges on the iron. And so 2 positive charges means it's going to be named iron 2 with the Roman numeral 2. So it's going to be iron 2 perchlorate, because whenever we have a polyatomic ion, you just use the name of the polyatomic ion as it is. So that's iron 2 perchlorate, and that's a type 2 ionic compound. And that's the last one.